us doing with Lab Night at Home. First, we're just going to look at the purpose of this lab, which we just took into account the two-dimensional motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. During this lab, we used the fundamental principles to predict our motion, which was the momentum principle, or Newton's second law, and the energy principle of thermodynamics. So the first thing I did was take the video that Dr. Greco gave us and exported it to Tracker. I set my origin at this fixed point up here, and my relaxed length of the spring, which is my calibration stick, I set equal to 0.7 as stated in the video. I started my video right whenever he releases it from his hand, and then I tracked my center masses. I got over about 100 data points, so once that finished running, I took what I had got and went over here to Excel and pasted them and just saved that as spring mass data, which I'm later going to use in my VPython code. So once we bring up my Python code, this was the one that we had wrote last week in lab, and I just made some changes to it. So the first thing I did was set my ball mass to 0.402, and I set my initial position to the very first values that I got in my tracker data, which was negative 0.105 and negative 0.606. Right here, the spring mass data 2D, that's all my data points in Excel, so it's gonna take into account those. My relaxed length of the spring is 0.118, and my spring constant is 6.78, and I found those using Hooke's law. So my delta T was 1 over 10.5, as they had stated in the video. Then if we go down here to the bottom, this was the code that's going to show the two different balls, ball 1 and ball 2. Which is our model, and one which is the simulation. So we're going to look at the X one right now. So when we run this model, okay, so here we notice it running, and you're going to see the graph over here is outputting a green line and a red line. So what happens when we take into account the Y, if we do this as the ball dot position from Y? So we'll just go over here and change these. And we're going to run that. As you can see, our graph looks a little bit different from the very first one. So going back to our PowerPoint, we're going to show that, okay, our green line in our graph is going to represent our model, and then our red line is going to represent our simulation. Our blue ball is the weight from the tracker video, and the orange ball represents the simulation mass. So we use these graphs to find the period of oscillating masses in the X and Y directions. We used one max point to another max point, which is from trough to trough on the graph, and we rolled our mouse over the graph to find the different time differences of these simulation periods. So that kind of answered our first question over here. So we got our first one to be 1.492 seconds, and our simulation to be 1.482 seconds. There's not much of a difference there, it's just 0.01, so that proves to be very well. Our X oscillation was a little different. We had a difference of 0.49 seconds, so it's a little higher, but still not bad. So moving on to the second question. So with our new choices system, what was the work done by the surroundings, and is the energy principle satisfied? So we know that our new system incorporates the ball, the earth, and the spring, and there's not going to be any outside surroundings that are going to make any significant change, and we know that no work is going to be done by these surroundings. This is because for work to be done, the energy has to leave the system and go into a surrounding object. So the energy principle is satisfied because our change in energy is going to be 0, and all the energy is going to remain in the system. So number 3 on the what does it mean? Here it was just asking what happens if we're going to change our point of origin. And what happens when we do this is We know that the sum of all the energies will be less than the sum of all the energies at the origin's original location. This is because the potential energies has to do with interacting objects, so you're going to get different values based on your origin choice. Overall, it shouldn't affect it too much, but we know that the physics of the system isn't going to change, and the change in energy qualities stays the same. The object's going to stay the same, it's going to behave the same way, and our graph is going to stay the same. So our main result for this lab was to prove that the energy principle, Newton's second law, and the conservation of energy were all demonstrated in this. We know that the change in energy is equal to the work done by the surroundings. So when we include the ball and the earth and the spring in our system, our delta E is going to be equal to 0 for all of our cases. Therefore, the origin isn't going to change the physics.